So do you see this, the show, the slides actually running?
Yeah.
Yeah.
Right, this paper is about a climbing robot to perform X-ray radiography of wind blades. This is our team. I'm Tariq, Sattar. I run this innovation center, the London South Bank Innovation Center. We are at the London South Bank University. But part of this robot was developed by a company called Fourth Engineering in Cumbria. Peter, Routledge, and Karen Markham were the people working from that end. So the introduction to this topic really is that there is wind power is, expanding by the day. The target in the European Union is that there will be 25% of all power generated will be green by 2022. And there's an aim to reduce the carbon dioxide emissions by 40%. It's a big capacity and is growing all the time. At the moment, there are about 700,000 blades in operation. Blades fail. They're high inertia systems. They experience high stress, wind gusts, weather, ice, etc., especially offshore. And they cause blades to fail. So on average, there are about 4,000 blades that fail annually, and the cost is huge, from 70,000 to 700,000 for each blade, depending on the size of the blade. And so it's becoming mandatory to inspect these blades every 3 to 4 months and maintain them every 6 months. And most of the inspection is done manually by people climbing on ropes to access the blades. And there are fatalities, lots of accidents, and the aim is to prevent those. And also, it is estimated that there will be a shortage of 28,000 qualified NDT operators, because you don't just need to operate the NDT, you need to climb up and get rope access to the blade. So you need to be something of a mountain climber. So our objectives on a number of projects have been to develop robotics that can provide you access to the blade. And this project called W Inspector built a robot that was winched up the tower using lifting equipment, that's winching systems that are on these systems anyway, and then reach across with an arm to use shearography to inspect the blade. But the present project that I'm going to describe is about a different way of doing it. That is to create a ring, lightweight structure weighing about 120 kilograms, with a bridge that two arms that open and close the blade, and 4 crawlers take the whole system up the tower. There are these arms which move from the ring structure to the crawlers and push the crawlers into the blade. So the crawler design is something like this. Simply put, it's 2 brushless DC motors driving rubber tracks on either end, and these are on gimbals so that you can twist the track to adapt to different diameter sizes of towers. There are lines of magnets arranged around the tracks which pull the track into the blade, a tower surface, to give you additional traction. But then the arm that is attached here on this plan view, bolted through these 4 holes, pushes the robot down. And then we have additional pneumatic cylinders, 4 of them, placed around the system, which push the tracks down. That's our construction of 4 robots, and we have tested them on the ground to make sure that they all move in a straight line simultaneously with the same trajectory. There are lots of actuators carried on board the robot. So the crawler has 8 brushless motors, 16 pneumatic cylinders. There are 4 pneumatic piston cylinders, which are the arms. There are 2 linear actuators which rotate this these arms by plus and minus 8 degrees in the horizontal plane to orientate the crawler correctly. There are two stepper motors which move, open and close the right-hand side and left-hand side of the bridge arms. And then there are two stepper motors which move an X-ray source on drive systems, belt systems here, source here, and actuator here, detector here. So that needs to be controlled, and we need to try to minimize the umbilical because, you're climbing up to great heights, 30 meters or more. And therefore it's important to keep the umbilical as small and as lightweight as possible. So our approach is to provide the DC voltage that we need on board by using 240 volts, 332 amp power line, which is shown here, which is an armored cable, then a three-way splitter, which splits the voltage and supplies 3 TDK power supplies, each giving out 24 volts DC and 67 amps each. These are then put in parallel to a distribution board, and that way we get a 24 volts DC bus, which is able to supply up to 200 amps to meet the requirements of all the devices. The control system similarly uses a CAN bus to control all the devices from the ground. We have a speed goat target controller, this one, which sits on the ground. We have a CAN module here in this slot and a CAN cable, and that will be the umbilical plus the power supply, which goes to a device, a Maxon device, which controls the motors, each one motor, using Hall sensors as the sensing device. And then we daisy chain all the devices that are on board to get the control system built. The state transitions are basically trying to send CAN commands to disable power, then to go to a power-enabled state, a pre-operational state, and then an operational state to which applies torque to the system. And you can return back from any state that you're in to any other state that you desire, plus a quick stop active, quick stop control, and fault reactions. So that is all encoded with the CANopen protocols. The commands to shut down, for example, is that. And these have to be worked out very carefully for all the different types of commands that you want to send. Our GUI for the system, it looks like this. We control sets of motors. So since the 4 crawlers have 8 motors and they all need to be moved in exactly the same way, we have only one panel which does that. So we can move progressively from voltage enabled to pre-operational to operational. That way we can make sure that we are not running away with things. But also we have diagnostics. So we read the status word to all the devices, all 8 devices, by checking the bits to see whether the device is actually enabled or not. If they're all green, that means everything is functioning correctly. That is important when you're working remotely because you can't see things. So you need to be able to visualize this here. And we do that for the different sets of motors. These control the bridge motors, these control the X-ray motors. And we also have diagnostics. So we are able to look to see what the status of each device is on these displays. So there are 8 of them, so we are able to see that. So that's the control strategy, and we can change the target by putting in a target here and just pressing this button to give a new position. The control method that we've used is a very quick, rapid prototyping type of approach using Simulink as the control mechanism. The advantage is that you just have block sets with state charts in which you can quickly see exactly what you are doing and change the bits that you need to change without writing lots of C++. And in this case, we have specified a trajectory where we specified the acceleration, the profile velocity while the system is moving to reach the target position. In this case, the target is 1,000 increments. And there are two curves here. Actually, one is the desired trajectory computed by the control devices, and one is the actual. And so there is very little error. This green bit is the error, but that is, the scale is 1 increment per division. So there's not much of an error. And that is, this particular profile is used on all the devices. So here is simply a video of a test that we performed. So there is a mock-up of a tower. This is 3.2 meters in diameters. This is our GUI talking to the target system here. And we simply first test to make sure that all the tracks are rotating in the correct way. Since there are 8 tracks, you need to be sure that they are all going to move in the same direction. And then we do the actual test to climb the machine. Now the bridge is missing here because Fourth Engineering had dismantled that because they needed space for something else. So we are only testing the ring being picked up and climbed. And we are climbing short distances at this stage, just 200 millimeter positions. And if you sort of watch this point and that point as the reference points, you can see that it does climb. And it maintains its position till we are ready to bring it back to rest on this scaffolding. This is the resting point. Okay, in conclusion, the aim was to develop this lightweight, easily transportable modular climbing robot, which could be taken offshore to a wind turbine tower and assembled quickly around it. We attempted to minimize the umbilical weight and size by using a CAN bus. So it's just a single cable, one for power and one for the communications. And we've tested all the control systems. There are 14 actuators, 22 pneumatic actuators, etc. So all these have been tested, and the climbing capability of the robot has been tested as initially on a mock-up of a steel tower. We have a parallel sort of partnership, which is doing work to develop a portable X-ray system, image detection systems using machine learning, artificial intelligence networks to automate defect detection, but I'm not reporting that here. And we will take this thing to a 30-meter tall training tower in Blythe to start testing this in earnest. Thank you very much. So any questions?
Well, hi, Tariq. Hi, it's Clive Lachlan here.
Hi, Clive.
Hi. Yeah, very, very interesting presentation. Thank you. It looks like a really good, fun project. I've got a few questions, and the first is, why did you opt to go for a system that crawls up the mast as opposed to sending up a sort of a lightweight structure, then winching the platform, inspection platform up?
Well, one of the reasons is that not all turbines have these winching systems in the right place. Some of them have it on the other side where the blades are. So you cannot always use a winching system. So here is a self-climbing system. That was one reason. The other reason is you can distribute the load of the whole system around the tower, which is helpful because we can put things like the TDK power supplies on the other side of the bridge. And that gives us a balanced mechanism. it could be improved. I mean, I have ways now. I've thought of ways to make this, to distribute the load in a better way. So that is one reason.
Fine. And also, you've opted for CAN bus. Have you considered wireless communications? You know, to just you know, so you just had to have power cable going up to the system.
Yes, though, obviously that's possible. But the problem again is wireless is not always very reliable. You lose communication. You know, they're using IP addresses, and so you can lose that. There could be conflict with other systems in the area. This is actually a much more robust way to do it because it is in that cable, and you can, you know, reset everything if you want to in one go by sending one, what is called a network management command. You can reset the communications, you can reset the each device, each control device. So it's a much better way to do it, I feel. And it's not a great deal of a twisted pair.
No. Yeah. And finally, if I may, are all these towers, are they always made from steel, or I'm basically thinking, is it magnetic?
Yes, they're steel. And we are not relying on the magnetic system. We found that afterwards it's really a hindrance. What you need is to have the arm that I showed you earlier, simply pressing down on the thing. And we are operating these pneumatic arms at 8 bars, and they apply a huge amount of pressure. So you get traction on the rubber there very well.
Yeah. Fine, very good. Thank you very much. Thank you.
All right, thank you. Okay, so that in my sort of wearing my hat as the chair of this session, we conclude this session. Thank you very much to all the speakers for contributing and all the questionnaires. Good session. Thank you.